Kinematic equations derived from calculus. I want to start by reviewing how to take the derivative. Let's say we're dealing with a function as a position of time, perhaps just written as x, and that's equal to some coefficient multiplied by the variable t to an exponent of n. The derivative of this function would be equal to the n comes down to the front, so we get n multiplied by that coefficient multiplied by the variable t to an exponent of 1 less of where we started. An example of this is, say we're dealing with a position of a function of time equation that was equal to t, and your goal was to take the derivative of that. Well, the t in the original equation here has an exponent of 1. So when we take the derivative, that 1 is going to come down to the front here. That's going to be multiplied by the variable of t, but the exponent of t is going to be 1 less. So that's going to be equal to 1 times t to the 0, or just 1 times 1, or simply just 1. So your derivative of this function is 1. Now, what if I wanted to work my way backwards? What if I wanted to, instead of taking the derivative, I wanted to take something called the antiderivative? So I started with my number 1. The variable I was dealing with is the dt, and I'm going to integrate from my final time, or rather from my initial time at the bottom to my final time. And so what we're going to do is take the antiderivative of 1, or what function, when I take the derivative of it, gives me 1. And we just did that. That ends up being t. And I still needs to be evaluated. So when we do that, we look and we plug in our tf for t, and we subtract our ti, and we also, don't forget, we need to add something called the arbitrary constant. And we get this expression that says it's equal to our change in time plus our arbitrary constant. If my initial time was at time 0, if I started at time 0, then it's simply just my time at my final time, or my time plus my arbitrary constant. Let's do another example with an antiderivative or an integral. And let's say we're dealing with the definite integral of t dt with the limits of an initial time to a final time. So if we take the derivative of a function and the answer gives us t, what function was that to give us t? Or what is the antiderivative of t? Well, that ends up being 1/2 t squared. In other words, if I took the derivative of 1/2 t squared, the answer I would get would be t. Now all I have to do is evaluate this by plugging in the limits, and don't forget your arbitrary constant there. And I get an answer of 1/2 multiplied by my final time, the quantity of my final time squared, minus my initial time squared, plus my arbitrary constant. Okay, now that we've had a review of derivatives and integrals, I want to talk to you about a process called separation of variables. And we're going to use this process to derive the kinematics equations. So let's go ahead and start with the value of instantaneous acceleration. So instantaneous acceleration is equal to the derivative of a velocity as a function of time equation or function. Or we could write that as dv dt. Now, separation of variables separates the dv and the dt. So what we're going to do is multiply both sides by the dt. And when we rewrite this, we will get on the left side a dt is equal to dv. Now, if we integrate both sides of these equations, we would write it like this. Notice my a comes out in front of my integral sign because it's a constant. And I can make it a definite integral by plugging in my limit values. The left side of the equation, I just bring down that constant. Now, what is the antiderivative of dt, which is basically what is the antiderivative of 1? Well, that gives me the variable of t. I still need to evaluate this. And don't forget my arbitrary constant. On the right side of the equation, what is the antiderivative of dv, which is basically 1? That ends up just being v. And plugging in our limit values here, arbitrary constant. Now, if you notice for arbitrary constant here, that will cancel. So we won't be dealing with the arbitrary constant much more. We still want to evaluate this. So on the left side of the equation, I'm going to get a times the quantity t sub f minus t sub I is equal to, on the right side, v sub f minus v sub I. If you look at this equation a little bit closer, or if we solve for v sub f, for example, in other words, multiply both sides by v sub I, what do we end up getting? I get v sub f is equal to v sub I, we're going to add that, v sub I plus a delta t. So this, folks, is one of our kinematics equations derived from calculus. Okay, let's derive another kinematics equation, starting with instantaneous velocity. So instantaneous velocity, of course, we could write it like this, and that's equal to your derivative of a position as a function of time equation. So we're going to use the process of separation of variables by multiplying both sides here by delta t, and of course the delta t's cancel. I'm going to rewrite this with my instantaneous velocity in the front. Dt is equal to dx. We're going to go ahead and integrate both sides, defining our limits here. So we have a definite integral. Okay, on the left side of the equation, I'm going to have the antiderivative of 1, which is t. And that's going to be equal to the antiderivative of 1 in this case would be x. Of course, this simply gives me v multiplied by delta t is equal to delta x. We know v, of course, is equal to delta x over delta t. Everybody's happy. But we can actually use the same process to derive, like I was saying, the kinematics equation. So we're going to do this again. Again, starting with instantaneous velocity, which is equal to dx over dt. Multiply both sides by dt. I'm going to have actually what I did here is went ahead and expanded the integral. Notice I also dropped the subscript of I for initial as well, which is okay. And now I will go ahead and integrate. So what I'm going to get here is vt plus, this one here is actually going to be a times 1/2 t squared. One way to know if you took the integral right is look at your answer to your integral, take the derivative of it. So the derivative of 1/2 t squared is t, and look up in the above integral and say is the the derivative of that, and it sure is. So the derivative of 1/2 t squared is t to the first power, and that's what I have, so I know I did that right. The right side here is just going to be x. Now I can always evaluate these here. Say I will go from t final, t initial. So I wrote in the limits from initials to finals here, so that I get an answer of t final minus t initial plus 1/2 a t final squared minus t initial squared equals delta x. Now simplifying this just a little bit further, I get delta x is equal to v delta t plus 1/2 a delta t squared. So this is another kinematics equation. If you wanted to go ahead and put back the little I here for v initial, because we know in this equation that is our initial velocity, that is fine. Now in deriving the third kinematics equation, I want to go ahead and look at your instantaneous acceleration and divide that by your instantaneous velocity. Now, as you recall, acceleration is your derivative of your velocity as a function of time, and your velocity is your derivative as a position as a function of time. And if you look closer, you'll see that the dt's cancel, and really what I have is an expression of dv over dx. And what I want to go ahead and do is separate the variables. So let's rewrite this as a over v is equal to dv over dx. Let's go ahead and multiply both sides by dx. And I'd like to multiply both sides by v. We'll do that in the next step. So I have a dx over v is equal to dv. And then let's multiply both sides by v. And I get a dx is equal to v dv. Now in this case, when we integrate, we're going to keep a as our constant. That will stay out in the front. And what I'm going to get when I integrate this, I'm going to get a delta x on the left side, and on the right side, I'm going to get 1/2 v squared Let's put in here a limit of v final and v initial. So we have a v final here, v initial here. So I have a delta x is equal to 1/2 v final squared, 1/2 times the quantity of v final squared minus v initial squared. Solving this equation for v final squared, I get it's equal to v initial squared plus 2a delta x. Here it is. Nice. So let's do an example. The speed of a bullet as it travels down the barrel of a rifle toward the opening is given by the equation I have here, where v is in meters per second and t is in seconds. The acceleration of the bullet just as it leaves the barrel is 0. For A, determine the acceleration and position of the bullet as functions of time when the bullet is in the barrel. In other words, find the acceleration as a function of time using the above equation, and find the position as a function of time. Part B. Determine the time interval over which the bullet is accelerated. Remember that the acceleration of the bullet, just as it leaves the barrel, is 0. Or in other words, when your acceleration is equal to 0, you can solve for your time to find your final time. Part C. Find the speed at which the bullet leaves the barrel. Find v of t when t is equal to 0.003 seconds. And lastly, for part D, what is the length of the barrel? Or what is your position as a function of time when you travel a total time of 0.003 seconds? Thanks for watching.